The second derivative test is a method for determining whether a critical point is a local minimum or a local maximum. Now I'm going to discuss how to go about this. Here are three functions. The first thing that I want to do is to try and sketch the derivatives of these functions. So this is the original function, y is equals to f of x. Now what I want to do is to sketch its derivative, which means I'll start with this point here. We know that the derivative of this point will be 0. Okay. Now this point here, the derivative, now the gradient at this point is positive, so it will be and it's really high and positive. I mean, if you draw a tangent here, it will have a high gradient, which means this point will be somewhere here. Okay. Now at this point here, the gradient will be negative. Okay. So basically what I mean is the gradient of that point is 0, the gradient of that point is positive, and then the gradient of this point will be negative. Okay. So somewhere around here. And if I choose to draw a line passing through these points, the line will look something like this. Okay. Something like that. Now what I want you to understand, one thing is this. Okay. This graph here, what we have here, the graph that we have here is a linear function. Okay. This is a linear function, and it's because here we said that the first derivative of a quadratic function is a linear function. Okay. So if you find the first derivative of a quadratic function, it's a linear function, and that's why here I have this as my gradient function. Okay. So the linear function represents the gradient function of the original curve. Okay. And you can see where it's passing through. It's passing through 0. Why? Because we know that at this point here, okay, which is corresponds to that point, we know that the first derivative is equals to 0. We know that at this point, first derivative is equals to 0, which makes sense. Okay. And that's why on this graph we can see that the first derivative is equals to 0 at this point. In fact, it would make more sense if we write that below here. So we can write here first derivative is equals to 0 at that point. Okay, this point here. And we can also notice that if this is the first derivative, then it means that all along this curve, the second derivative is negative, because the gradient of this line will be negative, which means that the second derivative is less than 0 all through. Okay, so the second derivative is less than 0 all through. In fact, we can say the first derivative is equal to 0 and the second derivative is less than 0 all through. Okay, so we can just take that out and we can say the first derivative is equal to 0 at that point and the second derivative is less than 0. Now we can do the same thing on the right, which means the gradient at this point will be 0. Okay, the gradient at this point will be negative, which means way below the x-axis, so somewhere around around here. Okay, and then the gradient at that point will be way above, so somewhere here. Okay, which means if we draw our straight line, it will be something like that. So something like that. So there are a few things that I want to talk about here. Is that again, this is the graph of y is equals to f of x. Now, at this point, we can notice that at this point here, so at this point, we can see that f dash x is equals to 0, okay, because this graph here represents this graph here. This one is y is equals to f dash x, okay, and we can see that at this point the gradient function is equals to 0, and then we can also notice that at this point here, okay, the gradient of the gradient is greater than 0, okay, because this is a straight line. This is a straight line with a positive gradient. So we can say that at this point, the gradient of the gradient function is greater than 0. It's positive. Okay. Let's carry on to the last graph. Now, again, remember these points here. These points here. These are stationary points because the gradients at this point is equal to 0. So here we also have a stationary point, which means the gradient of this curve at this point is 0. How about at this point? What will be the gradient of this curve at this point? It's positive, so it's somewhere around here. It's positive. The gradient of this point here will also be positive, right? So somewhere around there. And the gradient of this point here will also be positive, which means it's somewhere around here. The gradient of this point here will also be positive, right? Which will be somewhere around there. So what you're ending up with is this function. We are ending up with a function that looks something like this. Okay, we're ending up with a function that looks something like that. And this function here is a cubic function. Okay, this is a cubic function, which is no surprise because we know that the first derivative of a cubic function is a quadratic function. Okay, so and it makes sense. Originally we had a cubic function, so this was the cubic function, this one, y is equals to f of x. But now what we've ended up with here, all right, what we've ended up with here is a quadratic function. Okay, but what's more important here? The most important thing here is this. At this point here, okay, we can notice that at that point, actually, I think it's better if I draw it on the other side. So at this point here, we can notice that the gradient is equals to 0, okay, because it's a stationary point. The first derivative is equals to 0. But also we notice that the second derivative is equals to 0, okay, because it's a parabola. That's actually a minimum point. So we can go ahead and say that, and the second derivative is also equal to 0. So here we are faced with different features of these functions. So we can generalize and say that in general, suppose x is equals to c, and let's call this point, these stationary points, x is equals to c. So this point here, I'll call it x is equals to c. Okay, here I'll call it x is equals to c, and here I'll call it x is equals to c. So at these points where x is equals to c, suppose x is equals to c is a critical point on the graph of y is equals to f of x. in the first case, on the first graph on the left, if the slope is equals to 0, okay, as you saw, and the second derivative is less than 0, then we have a minimum point at x is equals to c. So I'm just going to generalize that point here, below here, and say that suppose x is equals to c is a critical point on the graph. And when I talk about the critical point here, I mean the stationary point, okay, on the graph of y is equals to f of x, okay. Suppose x equals to is a critical point on the graph of y is equals to f of x. One, we can say that if the first derivative is equals to 0, like what we have in the first case, okay, if the first derivative is equals to 0 and the second derivative is less than 0, okay, then we can say that y is equals to f of x has a minimum at x is equals to c. Okay? And that is the first case here that we have here. Okay? We can see that the first derivative is equals to 0 at x equals to c. And we can also see that the second derivative, the gradient of this straight line, is less than 0, which means we have a minimum point. Now, we'll go to the second point and say that, well, how about the second case? Look at the second case. What do we have? We have the first derivative is equal to 0 and the second derivative is greater than 0. Then what do we have? We have a minimum point. So go ahead and say, oh, by the way, here you're supposed to have a maximum point, not a minimum, maximum. We have a maximum point. Okay, so here, if f dash x is equals to 0 and the second derivative is greater than 0, then y is equals to f of x has a minimum at x is equals to c. Now that's what we have in the second case. Okay, we can see that f dash x is equals to 0 and the second derivative is greater than 0 because the gradient is positive. So we have a minimum point. Okay, number 3, we can say that if the first derivative is equals to 0 and the second derivative is equals to 0 as well, like what we have in the third case. Okay, when we have that, then the test fails. Okay, it fails because we don't know. We don't know we have a maximum or minimum. It could be either. In some functions, you can end up with a maximum point. So the stationary point, the stationary point can be a local maximum or minimum or neither, like what we have here. Okay, which means if this happens, use the first derivative test. So if this happens, use the first derivative test.